Welcome back my dear students and participants for this course titled Multi-Criteria Decision Making. Very good morning, good afternoon and good evening to all of you. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur in India. So, the broader concepts which we are still continuing to discuss is multi-criteria decision making, multi-objective decision making, which we will continue in this lecture. Then go into multi-attribute decision making and multi-attribute utility theory. So, this is the 32nd lecture out of the 60 lectures whole course, which is spread over 12 weeks, and as we know that each week we have 5 classes, each class being for half an hour. The concepts which we will cover in this 32nd lecture would be, I will try, obviously if there is a spillover, as I said, we will go into the subsequent lectures. We will consider the concepts of Pareto optimality in 2D space, concept of Pareto optimality in 3D space, and try to highlight that with examples. So, the problem was rich farmer in India growing 4 crops, rice, wheat, bajra, maize, selling price, cost price given, then output per acreage for these 4 crops given, and all the constraints are given. So, based on that we had the revenue cost function, and revenue minus cost will give you the profit, remember that. Now, we come to the constraints. The constraints are, if you remember, 2% of the land has to be left for movement of tractor and so on and so forth. The total land is 1000 acres, 2% of that goes. So, you have to basically have 98% of that 1000 which can be utilized. So, this is the first constraint which I will put a dark yellow tick mark. The second one was related to that due to water restriction, rice cannot exceed the combined acreage of bajra and wheat, where bajra and wheat are the third and the fourth. So, it is a third and the fourth, or let me see. No, it is the second and the third, maize is the fourth. So, rice cannot exceed the sum of the bajra and wheat. So, it is basically x 1 is less than equal to x 2 plus x 3, second constraint. Third one is that wheat is the staple diet, hence its production should be more than 50% of the combined of rice, bajra, wheat. So, rice is x 1, bajra is x 3, maize is x 4, wheat was x 2. So, if I consider 50%, more than 50% are combined. So, combined is for first, third, fourth and more than 50% of that. So, it is 1.5 and x 2 is basically greater than equal to that. And we have mentioned that each crop has to be in minimum of 100 acres, but cannot exceed 400. So, this is the fourth. So, these are the 4 constraints. Now, let us come to the problem. The problem is we want to maximize the revenue, which is true, and remember we are only going to maximize the revenue, we have not considered anything of the cost till now. So, we want to maximize the revenues. Revenue function was, if you remember, 35,000 x 1 plus 28,750 x 2 plus 36,000 x 3 plus 26,400 x 4. Constraints which we had considered are all put here. This is the linear programming problem with linear objective functions, linear constraints. When we solve it, the value of x, the x 1, x 2, x 3, x 4 correspondingly comes as x 1 is 0, x 2 is 400, x 3 is 266 and 2/3, and the value of the fourth one is 0. So, technically the amount which is obtained for the revenues is 35,000 into 0 plus 28,750 into 400 for the second variable x 2 plus 36,000 into 200 into 266 into 2/3, where 266 and 2/3 is the third variable, and 26,400 into 0, because the fourth variable is 0. The total functional value for other revenues comes out to be 211 lakhs. Now, let us just double check the constraints are being met. So, 400 plus 266 and 2/3 is less than equal to 980, perfect. Then if I have the second one, so this is also being met, because the first variable x 1 is 0, minus 400 minus 260 and 2/3 is less than equal to 0. Then similarly, for the third constraint, it is minus 400 plus a value which is less than 400. So, minus 400 and a value less than 400 is less than equal to 0, and all of them, if you see x 1, x 2, x 3, x 4 are between values of. So, technically this value of 0 and 0 should have been met, but we are taking we are trying to basically maximize the functional value. When I come to the cost, now cost factor has a different implication. The cost factor implication is that we are not considering any revenues, we are only concentrating on the trying to minimize the cost. So, technically if I consider everything as a cost, so that means 33,200 is the cost factor for producing 1 unit or 1 acreage of the first variable, 30,500 for the second, 35,750 for the third, and 27,000 for the fourth. So, correspondingly the values which we will put. Now, technically if I see, if all of them have to be produced at minimum 100, so obviously the cost would be increasing in the theoretical sense. Theoretical sense, the costs are increasing like this. I have to produce 100 acres for rice, so that would be 33,200. So, there is a cost already. So, red color means negative, even though I did use red color in the other combination, but I did not mention whether it is a positive or negative, it is here specifically negative. Similarly, for if I produce at least 100 for the second variable or the second product, it was wheat, the cost will come out to be this. For the third one, again 100 minimum, the cost will come out to be 100 into 35,750, and the last one, which is x 4, it will come out to be this. So, this is the total cost component. So, considering if I do not produce anything, is the minimum amount of cost I can have. That means, do not do anything. The moment you start producing, this is a cost factor, because I have not considered revenues as such. So, generally with a value of 0, 0, 0, 0 for all x 1, x 2, x 3, x 4, the value comes out to be 0, cost factor. Now, consider the net loss function. So, obviously, you can consider from the net loss function and the net profit function. Why I am using the concept of net loss function and the net profit function is like this. If you see the two equations, which is revenues and costs separately here, this factor. So, I will use red for negative value. So, these are there are no sign here. So, actually there are costs. So, these are all negative flow, and and if I consider positive one as blue, or let us use the green one. So, these are all positive. Very interestingly, if I follow for the first variable, which is rice, if I take the values, so x 1 is common, if I take the differences, this will be positive. I am using green color for positive. If I consider the next variable, which is wheat, this is negative, because 30,500 is a cost which is more than 28,750, which is the revenues. If I consider the third, which is Bajra, it is positive, because 36,000 is more than 35,750. And finally, if I consider the maize, which is the fourth variable, here 27,000, which is corresponding the cost, is more than 26,400, which is the revenue. So, these are positive, negative, positive, negative. So, if I consider the profit function and the loss and the net profit and the less loss function, the signs would be reverse. So, this positive, which is green, becomes red, red becomes green, based on how you try to analyze. So, obviously, you will try to maximize your net profit, and when you are considering the net loss, you will try to basically minimize your net loss function. So, if I consider the net loss as the what is written here, so it will be basically the loss function minus the revenues, of the cost function minus the revenues. So, it was basically positive, negative, positive, negative as given. So, now this becomes net loss, means the first one rather than positive now becomes negative. The second one rather than positive, negative being positive. The third one rather than being positive will be negative, because there is a negative sign here. And finally, the fourth value rather than negative being positive. So, if you consider that also in any combination, the values would come out to be 0, because the moment you produce, it will basically be a loss, and furthermore all the constraints are met. If I consider the net profit function, so the values are just reverse, the negative becomes positive, hence I am putting a green sign, the positive becomes negative, a red sign, again a green sign, then a red sign, and the corresponding values for to see the net profit function is also 0. If we solve the maximization of only revenues with the cost as a constraint, now this is the point, if you remember, we had considered that for the goal programming or the concept of multi objective problem, the idea was this. I will write it here and then solve the problem accordingly. So, in case you had the maximization, which I will use the green color, sum max of f1 and sum mean of g1, and the constraints were given as, say for example, h1, I am not writing x, is greater than equal to b1, then h2 being equal to b2, and h3 is less than equal to b3. So, here what we will do is like this, we will maximize f1 and bring this g1 function, which was the minimization one, as a constraint. So, the g1 function has to be minimized. So, that means it cannot exceed a value of, say for example, b4. This b1, b2, b3, which are shown in black colors, are for the already existing constraint. This B4 which is shown in red colors is basically the so called value which cannot be exceeded considering is a minimization problem. So, if I consider a value of the cost, say for example 0, consider 0, it can be consider that it can be other values also. It can be, say for example, loss has to be less than equal to 200 or 500 rupees or 5000 rupees. So, based on the fact that I am taking the constraint of the minimization as in the from the objective function brought into the minimization, here the problem is the revenue function is already there. I will put a green mark. So, these are x1, x2, x3 revenue functions. The constraints are already there. I am putting a violet tick mark, and the minimization has been brought back into the constraint. I will put a red mark. So, it is 33,200 x1, 30,500 x2, 35,750 x3, 27,000 x4, and this is less than 0. So, that means I am considering this as B4. Similarly, for the less than type, so less than type is basically I am considering this. So, they are all less than type, and this being a combination of less than greater than, because actually if I consider any x's, so the actual equation would be xi is greater than 100 is less than 400. So, if I consider the concept of less than, they would go here, and if I consider this, so this would basically become the greater than type, because x1 is more. So, this would go into the greater than function. So, this manipulation of greater than, less than, equal to can be done very easily. Now, when I consider this, I solve it considering the constraint is 0, I get a value of 0 for all the x's, which is fine. The main question which I have not solved here, but we will discuss later on for other problems, is what if the value which is less than 0 can be considered as, say for example, less than equal to 500 or less than equal to, say for example, 5 lakhs, and so on and so forth. Would we be getting answers accordingly for that? That means a minimum loss has to be there, because due to some reason you have to produce, due to some policy decision by the government, and or you have to basically think that you should produce. There can be different reasons. So, based on that you will consider whether you want to maximize your revenue and what is the minimum level of loss you can sustain. Now, the question is, can this problem be considered where you want to minimize the loss and consider the constraint also includes the maximization objective function which was there. So, if I write it, it is now minimization of G1, because G1 was the minimization as per the concept or the nomenclature which you are using. You already have the existing 3 sets of constraints, which are H1 is greater than equal to B1, H2 is equal to B2, and H3 is less than equal to B3, and the objective function which was there on the maximization type, that comes here, it was f. So, it becomes f1 is greater than equal to some B4, because profit has to be, revenue has to be more, and losses were less than that B4 there, which was shown in the red color B4. So, in this case the problems would be which minimization would basically bring the objective function as minimization and the constraints accordingly. Now, The question is that we have not solved this for the case when you are bringing the objective function as maximization in one of the constraints. The question is that how would you choose these red before and green before depending on the problem formation. I am using the same symbol, but I am mentioning the color scheme. So, if you have watched the video, you would understand what I mean by red and green. Red was basically corresponding to the cost and green was corresponding to the revenue. Now, technically you can solve this problem and get an intuitive start accordingly. Like I will mention and we will consider that later on. Like solve the objective function first with what we written, that solve the minimization problem as a single objective function, solve the maximization problem as a single objective function, solve them, get the answer. Now, when we come and trying to basically put the so called multi objective case which we have written, for the case when it is max of f1 constraints h1 greater than b1, h2 equal to b2, h3 is greater than b3, and there is a part of g1 is less than equal to b4. This b4, which I will circle with violet color, is the not the exact value, it would be a relationship with the single objective function which we have solved. So, say for example, in the single objective function, obviously in this problem it was 0, the final value when you are trying to solve the minimization problem. Consider it was 2 lakhs minimum value. So, we will consider some value of more than 2 lakhs here in place of red before, solve the problem and try to check that when you consider in the constraint one of this objective function which was already there, what is the change in the first objective function which is shown in green here. Green means maximization. In the similar way, when you are trying to minimize the cost, minimization of the cost which is g1 and is red in color, and the objective function which is initially, which is the maximization, comes in the constraints. So, this would be f1 is now greater than equal to, that was less than equal to. So, here you have already solved f1 initially separately as I mentioned, bring that objective function maximization means it will be a little bit less than what you maximum you can obtain and solve this problem. So, in one case constraints are same, in one case you have this is the minimization problem. I am repeating it time and again, please bear with me. Your maximization f1 h1 b1 h2 b2 h3 b3 and g1 being less than equal to b4. So, the main idea is if you consider so called problem 1 and problem 2, which I am writing case 1 and case 2, there is a subtle difference between them how they look like. One is a maximization, another minimization, considering that we are including in the constraints the other part of the objective functions accordingly. Now, we solve the problem considering, which I mentioned, when we solve the problem considering the cost minimization with the revenue in the constraint. So, this what I was talking about, this I spent a lot of time in discussing in the last slide. So, it will highlight here. So, here is the minimization one. So, I am putting a red underlying for this. The constraints are all same. So, these are the constraint existing one. Only the new one which is being brought is basically the value of the objective function which was maximization, which will mark in green. Only thing is this value which is 211 lakhs, that can be changed, perturbed, and based on that I can basically find out what is the minimization of the cost which can be obtained. So, rather than having 211 lakhs, it could have been some value of 211 lakhs minus a delta value. So, delta can be very large here, just delta I am using as a symbol, and based on that I solve. When I solve it, the values here it is 0 0 for x 1 x 4, that is a different question. So, but the values which we get it is basically 400 and 266 and 2/3 for the values of x 2 and x 3. So, if you remember when we are solving the problem for the maximization problem, we got that. Based on then that when we put the values accordingly, we get the corresponding output as 217, that means is equal to basically 217 lakhs 33,333 and 1/3. Now, the question is, before we wrap up this class, the question is what happens if we have 3 objective functions already, max, max, min, something like that. So, let me put, I will only consider one already existing constraint, which I will use the red color, which I will use the black color, sorry. So, you have max of f 1, max of f 2, min of G 1, constraint was H 1 greater than B 1, H 2 less than B 2. So, this is equal to B 2, sorry. Equal to H 3 less than B 3. So, this was the problem. So, what we can do is like this, solve them separately, like we solve max f 1 as a single problem without considering max f 2 and min G 2. Then we solve max f 2 without considering max f 1 and max min G 2, and we solve separately min G 1 without considering max f 1 and max f 2. Constraints remain same for all this statement which I made just now. When we want to solve the so called multi objective case, it will become like this. The objective function first remains as it is, and we bring f 2 being greater than equal to B 4. B 4 is a value which the idea which can get once we have solved case 2, which I just wrote down and I erased. And this case G 1 would be less than equal to. So, this values less than equal to are the minimum values for G 1 and max value for B 4. This is B 5, and this we have got the idea after solving case 3, which I have just erased. And similarly, we can do the combinations accordingly. I will solve the problems accordingly, and with this I will end this class, which is the 32nd class. Have a nice day and thank you very much.